Yeah, thank you very much. So I'm very happy to have this opportunity to share our recent research using quantum computer for data assimilation purpose. And I'm Shunji Kotsuki from Chiba University. And in this study, so we are proposing using the quantum annealing machine for solving the data assimilation. And so my talk consists mainly two parts. So one is the concept of the quantum data assimilation, and which was published last year on NPZ letter. And so if you are interested in, so you can find my article in LPZ. And fortunately, so this is the most downloaded article over the past 1 year of this journal. Okay, so recently, so quantum computer have been rapidly developed in recent years. And these computers uses the quantum processing unit rather than the CPU or GPU. And so that such computer uses the quantum effect. So because of that, so it can employ the fast computations. And so here, this quantum effect includes entanglement or quantum tunneling or superposition. And currently, there are two streams of the quantum computers. So one is the quantum logic gate, so that puts the problems down into the quantum circuit. And it's considered to be used for wider applications, but at this moment, not yet impractical due to the NISC or error correction problems. And the other stream is the quantum annealing. So this is the hardware specialized for optimization problems. And while this problem can solve only Cubo problem, but this is practically available. And several companies produce such quantum annealers, such as by the D-Wave of Canadian company or NEC of Japanese company. So, so we plan to use this quantum annealing for their assimilation purpose. And for that purpose, so let me explain what is the quantum annealer. So this quantum annealer can solve a kind of problem known as a quadratic unconstrained binary optimization problem known as the QBO, or also known as the Ising model. So in this problem, so we need to exchange, reformulate our problem to be this form. So this is a Hamiltonian that will be minimized. And this Hamiltonian composes the two parts. So the quadratic part and the, like a one term. And but the point is this problem should be represented by the binary variables that can handle only 0 or 1. But suppose we have a problem formulated by this QBO, so we can put our, submit our jobs to the quantum annealers through the application programming interface. And this quantum annealers, so this control device regulates this magnetic force to emulate the problem that we would like to solve. And this quantum processing unit, so at the initial state, so the quantum superposition exists, and the upward and downward spins exist simultaneously. And so this annealing gradually resolves this quantum condition. And by gradually removing this quantum effect, so finally, so one static solution can be obtained, and that can be read out from this measuring device. And for these examples, so there is upward spin and downward spin, and so that can be read out from this measuring device to produce one result. But here, so we need to know about the quantum, like a quantum noise. So because of the quantum effect, so we are usually suffering from unavoidable stochastic noise. And therefore, so we usually employ this quantum annealing several times. And so the number of the quantum annealing is defined by this num read. This is a kind of tunable parameter. And so by every quantum annealings, so we can obtain the different result. But we can compute Hamiltonians for each result and select an output using the smallest Hamiltonian. So by this way, we can stabilize the answer from the quantum annealers. And so it means, so once we can reformulate our problem into QBO, so we can use this quantum annealer for solving the problem. And next, so let's think about how to reformulate the 4D bar to QUBO. And so this is, first one is a well-known equation of the 4D bar with inner and outer loops. And for the first approximation, so let's think about the 4D bar with only inner loop. So that means, so we keep using the tangent linear model and its adjoint around the first guess trajectory. So in this case, so the cost function can be approximated by this equation, and this is represented by this equation. So one matrix bounded by analysis increment, and a vector followed by analysis increment and constant. And so here, so this analysis increment is a real number. So therefore, so we would like to approximate again to change this equation to be QUBO. And for that purpose, so we have an additional approximation for binarization. And suppose, so we have a 4 qubit for handling one real number. Then, so this binarization, it uses a 4 qubit to handle one analysis increment. So in this case, this 4 qubit can handle the 16 integers from -8 to 7, and with a tunable like scaling factor, so we can handle real numbers. So this is a kind of rough approximation, but due to this approximation, so we can approximate our 4D bar problem by QUBO. So here, so we can represent the 4D bar's cost function as a Hamiltonian by this form. So by this way, so we can use quantum annealers for solving the problem of 4D bars. And so we employ the like a 4D bar experiment with Lorentz 96 model, so with 2-day windows, and supposing the every 6-hour like 4D observation. And so what we employ is the offline data assimilation. So we solve the 50 like 4D bar problems as an offline experiment. And so we compare the 4 experiments. So the first two is the conventional 4D bars with outer loop and without outer loop. And we solve these problems by the quasi-Newton method. And for solving the QUBO problems, so we use the two hardwares. So one is the simulated quantum annealer. So this is a GPU-based suit quantum annealer. And so what we used is a fixed as amplifies the simulated quantum annealer that can handle the 60,000 qubit. And the last one is the real quantum annealers, like provided by the D-Wave. And at this moment, so this computer have more than 5,000 qubit, but the available logical qubit is much smaller and only 170. And because we would like to solve the 4D bar of the Lorentz 96, so we is having the 40 variable. So therefore, so we can use only 4 qubit for handling the one real number. So, but so we tried to solve the 4D bar by using the quantum annealer. And let's see the results. And so this figure compares the root mean scalar like over the 50 data simulations with the 2-day windows and 4D observation, and the like background covariance is manually tuned. And so first one is a conventional like 4D bar with and without outer loop. And so we see the reduction of the root mean scalar against the first case. And the next two experiment is like a 4D bar solved by the like a pseudo quantum simulated quantum annealer or physical quantum annealer, and that also reduces the root mean scalar with respect to the first case. But we can see the slight degradation of the like a physical quantum annealer. So this is due to the stochastic noise, and I will explain it later. And so if we see the root mean scalar, the quantum annealer produces a slightly degraded analysis compared to the conventional method or simulated quantum annealer. But if we see the computation time, so we could reduce the computation time like drastically. So here we are comparing the like average execution time for one 4D bar, and So truth be told, so first two experiment uses the CPU-based like computer, and this one uses like a GPU-based simulated quantum annealer, and last one uses like a real physical quantum annealer. So therefore, so we can't employ the fair comparison, but we see the great reduction of the computation time using the quantum annealer, and this is one like a good benefit. But we also need to care about the stochastic noise in quantum data simulation. So here, so I'm showing the like a two result of the same 4D bar problem. So this is the first result and second result, third result, blah blah blah, up to the 10th result, and for the like first 8 variables. And as you can see, the physical quantum annealer provides much noisier results than simulated quantum annealer. So in the case of the simulated quantum annealer, so it keep providing the similar result. So even if this answer seems to be dissimilar, but if we can compute the this integer part, so the simulated annealer is saying that the result is 0 or -1, so that they are very similar. But in the case of the physical quantum annealer, so we suffer from the stochastic noise of the quantum effect, and the result can be sometimes very different, like such as 4 or 6 or -4, and that should be cared. And therefore, maybe increasing the number of the quantum annealing is important. And here, so we are like exploring the sensitivity to the parameter number of readout. And so here we are comparing the root mean scalar and the computational time as a function of the number of the readout. And by increasing the number of readout, so we can reduce the root mean scalar, because so we can select the better result yielding the smaller Hamiltonian. And while it increases the computation time linearly, so we can stabilize the result by increasing the number of the readouts. And another important thing is that there is a tunable parameter, like which is a scaling factor of this part. So again, so in our problem, so we represent an analysis increment with 4 qubit, and that can handle the 16 integers from -8 to 7. And in the case of alpha is 100, then analysis increment ranges from -0.08 to 0.07. And in the case of alpha is 10, then analysis increment ranges from -0.8 to 0.7. And so we investigated the sensitivity to this scaling factor for root mean scalar. And when the alpha is very large, in this case, the analysis increment can be very small. So therefore, the root mean scalar is very similar to the mean root mean scalar of the first case. And by reducing the scaling factor, so we can handle the wider range of analysis increment, and we can see the reduction of the root mean scalar. But as you can see, so there is a large discrepancy between the simulated quantum annealer and the real quantum annealer. And when alpha becomes small, then the range of analysis increment becomes large. So in this case, one stochastic noise of the 1 qubit can change the result drastically, and that may be problematic for quantum annealers. So therefore, so we can choose this scaling factor carefully for a quantum data simulation. So that's the summary of my first part. And for the second topic, so now we are exploring the considering the chaotic cost function using the quantum data simulation. And this manuscript is currently under review. And this research is made by Professor Tsuyuki of our university. And so we would like to find a better solution for strongly nonlinear 4D bar. And so this study illustrates the shape of cost function for the 4D bar problem Lorentz 63 model. and for regular and transition regimes. And so this manuscript illustrates the cost function directly as a function of the first variable. And in the case of the regular regime, so we can see the stable cost function. In this case, so we can find the optimal solution easily. But in the case of the transition regime, or when the 4D bar is within the strongly nonlinear regime, so the cost function becomes to be, how to say, very difficult to find the optimal solution because of the many local minima. And and we thought so we can use the quantum tunneling for finding the optimal solution for such problem. And for such purpose, so we propose considering the chaotic cost function in quantum data simulation. So again, so this is the cost function of the 4D bar. And so there is the analysis increment of the a case time slot. And usually the 4D bar considers only the first order approximation of this analysis increment. But so we can think about the second order approximation of the Taylor expansion. So in this case, so we can consider the second term of the Taylor expansion. Then the cost function becomes to be the chaotic with respect to the analysis increment. And in this case, so we can consider a cost function having the two local minima. So suppose, so this blue one is the real cost function, and the orange one is the approximated cost function having the two local minima. And so we can compute the minimization based on the gradient-based optimization, but the gradient-based optimization can be suffered from the local minima. But when we can employ the quantum data simulation, so we can use the quantum tunneling to reach to the better solution. And so this is the idea of this quantum data simulation. And in our proposed algorithm, so we first employ the quantum annealing to find the analysis, but because of the quantum annealing, so we can handle the discretized solution. So therefore, so we employed an additional a gradient method to reach to the global minima. So this is the idea of the quantum data simulation for using the quantum tunneling. And but you may wonder how we can treat the chaotic cost function by quantum annealing. And the answer is that quantum data simulation can solve polynomial binary equations. And it means beyond the quadratic unconstrained problems like 4D bars. And so let me explain an example, a simple example with 3 variables, having the Q1 and Q2 and Q3. And suppose we would like to minimize this Hamiltonian, having the Q1, Q2, and Q3. So this is a cubic function. And but there is a very famous trick to reformulate this Hamiltonian to be this. So with an additional dummy variable. And with this additional dummy variable, so we can reformulate this cost function by this form. And Q tilde and Q3, and an additional term, let's say this is E. And so if we think about the all combination of Q1 and Q2 and Q tilde for this part E, this E becomes 0 only when Q tilde equal Q1 and Q2. So it means adding this additional term E imposes Q tilde is always Q1 and Q2. And consequently, so minimizing this problem is equal to minimizing this Hamiltonian. And so this kind of extension can be applied for any polynomial binary equations. So therefore, so while the quantum annealing can handle only QUBO, so we can also solve the chaotic cost function of 4D bar. Okay, so and we tested this idea with Lorentz 63 model with long window having the many local minima. And so what we propose is an algorithm first solving the 4D bar with a gradient method, But if the cost function is higher than a threshold, then we employ the quantum annealing and followed by the gradient method. And if cost function is still higher than the threshold, then we finally employ the ensemble common filter. But in principle, so we employ the 4D bar and quantum annealing and followed by the final 4D bar. And so here we are comparing the like a conventional 4D bar and proposed 4D bar and quantum annealing. And we show the like cost function and root mean scalar for many like problems. And in the case of the conventional 4D bar, so 4D bar can be trapped by local minima. So therefore, so it produces many cases having the too high cost function and large root mean scalars. But by using the quantum annealings, so this kind of like issues like trapped by the local minima can be greatly solved. So and we can obtain the more stable solution with smaller cost function and smaller root mean scalar. And yeah, that's the idea of extending the quantum annealing for like 4D bar. Okay, so let me summarize my presentation. And so quantum annealing was applied to data simulations. So we have succeeded in accelerating computation for the bar by quantum data simulation. And also the quantum data simulation seems beneficial for avoiding local minima by quantum tunneling. So there are some problems such as unavoidable stochastic process in physical quantum annealing, and the available qubit is limited. But that may be a nice first step to use quantum computers for data estimation purpose. Okay, so that's all I have to say today, and thank you very much.
Thank you very much, Shunji, for a very interesting and thought-provoking talk about modernizing Bolivar and finding ways to make it more efficient. As always, everybody, if you have any questions, please put them in the Yopad. We have a couple more minutes before the session finishes. Oh. Okay. Oh no, here we go. Sorry. So the question comes from Takishi Enomoto. Can quantum noise be used to perturb observations?
Yeah, that may be a nice idea. And as far as I understanding, such quantum effect is a kind of pure noise, and therefore that can be used for perturbing analysis or perturbing observations, or like to handling the stochasticsness in their estimation. So we haven't considered how to use it, but there may be ways to use such quantum effect intentionally. Yeah, that may be a nice direction. Yeah, thank you for nice question.
Sure. Are there any other questions? If not, thank you again